In this section, we're going to look at what we call improper integrals, and we're going to extend the concept of the definite integral, which we defined in Calculus 1, to functions with either an infinite discontinuity somewhere in the interval of integration, or where the interval of integration is infinite. Here are three examples. Notice that the function 1 over x cubed is discontinuous at x equals 0, so it approaches infinity, and the fundamental theorem of calculus does not apply to b. And also, this integral just simply isn't defined because the function is not continuous on that subinterval. Also, with a and b, the limits of integration describe intervals that are infinite in length, and once again, the fundamental theorem of calculus does not apply, and our previous definitions of the integral don't apply. So our job is to come up with a new definition of the integral here, and we're going to start with an improper integral of type 1, which is going to be an integral of a function f of x on an infinite interval. And in part A, we're going to start with the integral from a to infinity of f of x, where the definite integral from a to t, where t is any number between a and infinity, already exists. So we can calculate that using our previous definition. So this definitely means that f of t is defined for every value of t between a and infinity and at a. And it also means that you can't have an infinite discontinuity for f in this interval. So you can't have a point where f goes to infinity or minus infinity in this interval. If you like, you can imagine that f of x is continuous. Probably for most of our examples, we'll apply this to continuous functions, but it also applies to functions which have a finite number of discontinuities in that infinite interval. Now, for our definition, we say that the integral from a to infinity of f of x dx in this case is the limit as t approaches infinity of the integral from a to t of f of x dx, if that limit exists and is finite. Otherwise, we say this integral is divergent. And notice that we're taking the limit of something that theoretically is well defined and we can calculate it, and of course we use our laws of limits to calculate that limit. Now suppose we want to integrate a function, a nice function, from minus infinity to b, and assume also that f of t exists for every t less than or equal to b, and that the integral from t to b exists for every t less than or equal to b. Then we define that integral as the limit as t approaches negative infinity of the integral from t to b of f of x dx. And notice we're defining this as the limit of something that's well defined. We've already defined it in Calculus 1. We're assuming they all exist, and we can apply our limit laws from Calculus 1 or our tricks for calculating limits to calculate that limit. The integrals from a to infinity of f of x dx and minus infinity to b of f of x dx are called convergent if the corresponding limit exists and is finite, and otherwise we say that they're divergent. Lastly, suppose we want to integrate a function from minus infinity to infinity. Then we pick a point a in the interval from minus infinity to infinity, and we calculate both integrals, the integral from a to infinity of f of x dx and the integral from minus infinity to a of f of x dx. And if both of those are convergent, we say that the integral from minus infinity to infinity of f of x dx is the sum of both of those integrals. Now we're assuming for now that the integral from t to a of f of x exists for every t less than a, and the integral from a to t of f of x exists for every t larger than a. So we're assuming f of x is well behaved and doesn't have any infinite discontinuities in this part. Now we must be a little careful here. When applying this, we must make sure that both integrals on the right-hand side converge before we conclude that the integral from minus infinity to infinity converges. There are other definitions out there for this integral, so be very careful that you're using the one we give you here in this course. Let's try some examples. Let's suppose we want to figure out whether the following integrals converge or diverge. So we have the integral from 1 to infinity of 1 over x and the integral from 1 to infinity of 1 over x cubed. And these are examples of the integral from 1 to infinity of 1 over x to the p, which will become a very important integral in our lives. Well, let's follow the definition. By definition, the integral on the left is the limit as t approaches infinity of the integral from 1 to t of 1 over x dx. And of course the rest are details. We know that the natural log of the absolute value of x is an antiderivative for 1 over x. So this is the limit as t approaches infinity of the natural log of t minus the natural log of 1. We also know that the natural log of 1 is 0. So this is the limit as t approaches infinity of the natural log of t, which is infinity. So the integral on the left diverges. Well, let's try the integral from 1 to infinity of 1 over x cubed dx. Again, we're applying the definition step by step. It should be the limit as t approaches infinity of the integral from 1 to t of 1 over x cubed dx. Now we find an antiderivative for x to the minus 3, which is x to the minus 2 over minus 2. And then we plug in our limits of integration. So we're looking at the limit as t goes to infinity of minus 1 over 2x squared plus 1 over 2. Now as t approaches infinity, t squared goes to infinity, so 1 over 2t squared goes to 0. And in fact, this limit is finite. It's equal to 1/2. So the integral on the right above converges, despite the fact that it looks very similar to the integral on the left, which diverges. And in fact, we can say the integral from 1 to infinity of 1 over x cubed dx converges to 1/2. Let's have a look on Mathematica at what's going on. We have a geometric interpretation of this infinite integral in this case. Since the integral from 1 to infinity of 1 over x dx diverges, we say the area under the curve y equals 1 over x on the interval from 1 to infinity diverges. It's not finite. And since the integral from 1 to infinity of 1 over x cubed dx converges, then the area under the curve y equals 1 over x cubed on the interval from 1 to infinity is finite. It's actually equal to 1/2. Now that's as much a definition of the area under the curve as it is a geometric interpretation of these integrals. Let's have a look at what's going on here on Mathematica. Suppose I let p equals 1 and I'm looking at the integral from 1 to infinity of 1 over x to the p dx. By definition, this is equal to the limit as t approaches infinity of the integral from 1 to t of 1 over x dx. So we see the graph of 1 over x here, and we already have this area interpretation of the integral from 1 to t of 1 over x dx. It's the area under this curve, which of course we know is the natural log of t. Now, as the t increases, that area expands, and in the limit, it would theoretically cover the entire area under this curve between 1 and infinity. And we can see that for p equals 1, this area grows very quickly. And we can definitely see that here in this applet where we show the value of the integral from 1 to t of 1 over x to the p. In this case, we're setting p equals 1. And now we can set x as large as we like. And you can see that this is going to grow without bound. So I'll add a few zeros here and we'll see that this grows, not very fast, but nevertheless there isn't really any limit happening here, but it keeps increasing. And of course, because it's the logarithm, it's not increasing very, very quickly. On the other hand, if we set the power of p equal to 3, then we see that this integral tends to reach an upper bound. And of course, that upper bound we know should be 1/2. So let's set p equals 3 here and see what happens as t increases. Let's add a few zeros. You can definitely see that 0.5 is an upper bound, and in fact at this point, as far as Mathematica is concerned, the integral from 1 to t of 1 over x cubed is 0.5. So it is very different behavior than the integral of 1 over x from 1 to infinity. This one converges, the other one does not converge.